So, hi. First of all, I've been neglecting the homework, and I'm basically overwhelmed with other things. But it's becoming unreasonable. So I will aim to write 2 more assignments. One tomorrow and due about a week later, and one about a week from now and due about a week after that. And then we'll have a total of 6 assignments, which is not the 10 that I promised, but, well, that's what I have, sorry. And that will be the basis for your mark. I expect the marks to be good, but there has to be something to explain it. So, okay. Second, you all have a copy of the handout, right? Good. So the topic for today is the 2 algebras that we actually work with, the ones that actually work, okay, as opposed to being, they're no longer demos, except CU is still a demo. It's the classical algebra, whereas the quantum algebra is the real thing, okay? However, it's worth spending some time understanding the classical algebra before going on to the quantum one. There's a lot to understand for both. Okay, so let's start with the classical algebra. So first of all, we did talk about Lie algebras before, right? And everybody knows what a Lie algebra is? Okay, so I'll quickly review what's a Lie algebra. So, so a Lie algebra is a vector space G with a bracket, so a binary operation, so it's a bilinear operation from from 2 copies of G into G. So if you want, it's a morphism from G tensor G into G. Which has 2 properties. So one, it should be anti-symmetric, and 2, it should satisfy, sorry, I'm running out of chalk. It should satisfy Jacobi's identity. So Jacobi identity, the Jacobi identity says that the bracket of x with the bracket of y and z, so for every 3 elements, the bracket of I with the bracket of y and with the bracket of x with the bracket of y and z, plus the 2 cyclic permutations of this, so y z x plus z x y is equal to 0. I should have written anti-symmetry explicitly too. So this just means that xy is negative yx. So these are super duper important. So basically, the reason is, or one reason why they're important, is because of Lie groups. So a Lie group is more or less, I mean, I'm skipping details, but it's a group which is also a manifold. And of course, the group structure should be compatible with the manifold structure. but I'm skipping the details, okay? It basically, can you pass this? And basically, the group of symmetries of physical objects tend to be Lie groups. So, like the group of rotations of R3, the group of Lorentz transformations, transformations that preserve the Lorentz metric in special relativity, and also lots of other physical groups that occurs in physics, or groups of symmetries, are of that type. So they're super important. And then, if you look at the Lie group, so I don't know, let's imagine a Lie group as a manifold which also has a group operation. Well, it also has a group structure, so it has an identity somewhere. And if you look at the tangent space to the identity, tangent space to the group at the identity, then it inherits some structure from the group G, and if you call it Gothic G, then it ends up having the structure of a Lie algebra. So Lie algebras, and it's kind of nearly reversible. So if you know the group, you know the Lie algebra. If you know the Lie algebra, you know a lot about the group. Not quite all of it, but you know a lot about it. So, so studying Lie algebras is, books and books and books about it. Okay? Anyway, just two examples of Lie algebras, not of Lie groups. So one example is just the n by n matrices, and then the bracket. So the bracket of two matrices is defined to be the commutator, so AB minus BA, and and you can check that it satisfies well, it's clearly anti-symmetric, and you can check that it satisfies Jacobi. It's just a matter of plugging in here, and well, it satisfies Jacobi. And the second example is SL2. So SL2 is actually a subalgebra of M 2 by 2. So these are the matrices in the 2 by 2 matrices whose trace is equal to 0. So basically these are matrices that look like A minus A, B, C. And you can check that the commutator of two such matrices is again a matrix like that. And hence it's a subalgebra of the 2 by 2 matrices. This is an informal language, but this is sort of the mother of all the algebras, mother of all Lie algebras, because well, it's also a lie, but it's a very, very important Lie algebra because in some sense it's the simplest of the more complicated Lie algebras. Okay, and all the more complicated Lie algebras are in some sense made by gluing together many copies of SL2. So in fact, if you look at the n by n matrices, you can view the n by n matrices as somehow a gluing of many copies of SL2. Though I'm being a bit informal. I'm not saying how, I'm just saying it's significant. The reason I'm mentioning it is because our algebra is a variant of SL2. It's not quite SL2. Okay? Anyway, so let SL2 plus epsilon be the Lie algebra. Well, it's a 4-dimensional Lie algebra, so it's definitely not SL2 because SL2 is 3-dimensional. There are only 3 parameters here. Nevertheless, they're relatives, and it has 4 generators, y, b, a, and x. And notice that I'm using boldface letters for the generators, following the convention I had before, that boldface means non-commutative. Sorry, when I did it on the board, I said I put hat on top of the non-commutative things, and now I'm just making them boldface. So boldface means things that do not commute, and later there will be commutative versions of these letters. Anyway, and then there are, and then the bracket is defined by the bracket of A with X is X, the bracket of B with Y is minus epsilon Y, the bracket of A and B is 0, and so on. And this forces all the other brackets. So for example, if you want the bracket of Y with X, then by anti-symmetry it will be negative the quantity written here. Okay? Now, in principle, you have to show that this satisfies the Jacobi identity. So one way to do it is to go over all possibilities. So basically, x, y, and z can be any one of y, b, a, and x. So it's a finite number of possibilities to check, and you check, and all of them and they all satisfy. So this satisfies the Jacobi identity. In a minute, we will see a different way to do it. Not later, we will see a different way to do it. Okay. By the way, my purpose right now is to just to introduce the algebras, say a few words about them, and then we still have a little more time to study them. But at the moment, I'm just introducing them. Anyway, this is not yet CU, the algebra I care about. The algebra I care about is the so-called universal enveloping algebra of SL2 plus epsilon. So CU is the universal enveloping algebra of SL2 plus epsilon. So what is a universal enveloping algebra? So maybe I'll say a bit abstractly. So whenever you have an associative algebra, it's automatically it's automatically also a Lie algebra. So if A is an associative algebra, you can define the bracket of x and y to be xy minus yx, and then the exact same verification that I didn't do here, I will not do here either, but it shows that this is a Lie algebra. So this is defines a Lie algebra structure on A. And then you can ask yourself, is every Lie algebra a subalgebra of an associative algebra? A sub-Lie algebra of an associative algebra? And the answer is yes. And again, there might be better definitions for. I think I don't want to go through the whole development, so I'll skip some some things. But the answer is yes, and the algebra A is defined as follows. So if you want to go from a Lie algebra G into an associative algebra, so what you do is you call that associative algebra the universal enveloping algebra of G, and basically you need to allow products of the elements of G. Okay? So you just allow all products of elements of G. So you just define it to be the set of all words in the alphabet. Is this how you spell alphabet? I don't know. No H, right? Okay. In the alphabet G. Modulo, okay, I'll tell you in a minute modulo what. So, but basically what does it mean? It means that if G is, say, the Lie algebra generated by Y, B, A, and X, as is the case for us, then U of G will be made of all words of the form Y, B, A, made out of these letters. So B, X, X, Y, A, B, X. All such words, except you want to mod out by two relations. So first of all, you want, with multiplication, so the multiplication is simply concatenation. So if you have two such words, you multiply them by just making a longer word, okay? Concatenating the two words. But you want multiplication to be bilinear, so you mod out by the relations that forces this. But this basically means that it's multilinear in the letters. So if you replace x here by 7x plus 3y, then, this is still an element of the Lie algebra, so it's still a single letter, but you want to allow to expand, okay? So you mod out by multilinearity in the letters. Okay, and the other thing you want is you want the universal enveloping algebra to include, to somehow include in it the original algebra. So you want whatever relations the original algebra had, you want the same relations in the universal enveloping algebra. Basically, you want this to hold. So you mod out by the relation that the bracket of x and y, so is equal to xy minus yx. So the bracket of x and y is a single letter word, right? Because this is a letter, this is an element of the Lie algebra, this is an element of the Lie algebra. The bracket is again an element of the Lie algebra. So this is a single letter word. And then this is the difference of two letter words. So you just decree that this single letter is equal to this linear combination of two letter words. And you want the ideal generated by this. So you mod out by the ideal generated by these relations. Okay? So basically, maybe I'll give an example. Sorry, it's going. So maybe I'll give an example So you could take the Lie algebra to be the Lie algebra generated by two generators, P and X. Sorry, I suppose I need three generators. So P, X, and let's call the third generator T. Modulo the relation, so sorry, with the computation relations that P bracket X is equal to T, and T is so-called central. So the bracket of T with anything else is 0. So T with P is equal to T with X is equal to 0. And then the universal enveloping algebra of G is more or less the Heisenberg algebra that we talked about before. So basically you allow, so let's think about it a little bit. You allow words P, X, X, P, P, T, T, P, X, whatever. And you have the relation that Px minus xp is equal to t, and that Tx is equal to xt, and Tp is equal to Pt. So this means that the t's commute, so you can bring them to the front. And then you just have words in the p's and the x's, and that's and then the p's and the x's satisfy this relation. So that's very similar to what we call the Heisenberg algebra in class before. In fact, if you look at the universal enveloping algebra of this G and mod out by the further relation t is equal to 1, namely t is equal to the identity of the universal enveloping algebra, which is just the empty word. Okay? So if you mod out by this further relation, then this is the Heisenberg algebra that we talked about before. Okay. Okay, and one last thing is that you always have a map from the Lie algebra into the universal enveloping algebra. Basically, you map the Lie algebra to single letter words. Okay. So Cu is the universal enveloping algebra of SL2 plus, and Cu has a multiplication operation, namely just the concatenation. So there is a multiplication operation from Cu to Cu into Cu. And in fact, I claim that it's a Hopf algebra. But this requires a proof. It requires definitions and requires a proof. So basically, I am telling you that there is a unit, which I will call C eta to distinguish from Q eta. There is a co-unit, there is an antipode, and there is a coproduct. And here are their definitions. So the unit applied to a scalar lambda just gives you lambda times the identity, where again the identity is just the empty word. Okay. The co-unit, so I just have to tell you how the co-unit acts on each of the one-letter things. The co-unit is supposed to be multiplicative. So if you have more than one letter, you just product. You just apply the co-unit to each of the letters and multiply. But anyway, as it turns out, it's very easy because the co-unit applied to every letter is 0. However, applied to the empty word, you get 1. That's forced, I suppose, because if it is to be multiplicative, then it has to be 1 on the empty word. Okay. The antipode maps each of the generators to its negative, and the coproduct maps each of the generators to basically each generator gets to decide whether it goes to the left tensor copy or the right tensor copy. So the coproduct applied to y, the coproduct applied to tensor factor I, applied to y in tensor factor I, is you put y either in tensor factor j or in tensor factor k. So a different way of writing it is to say that the coproduct of any generator z is z tensor 1 plus 1 tensor z. In principle, I have to check that all the conditions are satisfied. I will not. It will actually follow later. Okay. I think I'm only introducing it just so that we have names for things. I mean, the work will come later. And the next thing I want to say is, well, I'm not even saying what is a quantization, but QU is a quantization of CU. And what it is it's the associative algebra on the same collection of generators, except now I'm allowing a formal parameter h bar, a perturbation parameter h bar. The relations are a bit different. So A commute with x is still x. B commute with y is still minus epsilon y. A, B, well, some things are the same. The main difference is that x times y minus q times y times x is equal to 1 minus ab divided by h bar, where q is e to the h bar epsilon. Epsilon is the same epsilon as before. A is e to the minus h bar epsilon a. So in general, uppercase letters stand for the exponentials of the corresponding lowercase letters. So uppercase A is the exponential of lowercase a with some coefficients. And uppercase B is the exponential of lowercase b, again with some coefficients. Notice that this isn't a rational function. Namely, you see, when you expand this as a power series, it starts with 1. When you expand B as a power series, it starts with 1. So, and now I'm looking at 1 minus AB, so I get 1 minus 1 plus higher powers of h bar. So the 1 cancels, and I'm left with higher powers of h bar, and then it's divisible by h bar. So this is actually just a power series on the right, so it's allowed. Okay. Anyway, QU also has a multiplication operation. So the quantum multiplication is, well, simply the concatenation again. And it also has a co-unit, a unit, a co-unit, an antipode, and a coproduct. And they are given by the formulas written here, which are not the same as the formulas of before. The first two are, but the later two aren't. Okay. Next, so again, I'm only introducing the creatures. I'm not saying much about them yet. I will start saying stuff about them in a moment. So the next thing is, I claim that there is an R element in QU. Namely, there is an element Rij in QUI tensor QUJ such that Rij and the Hopf structure satisfy all the axioms we want. Now, here's the formula for Rij. I mean, I have nothing good to say about it. At some point it will follow, but at the moment it's just a formula. Okay? Anyway, but I do want to say a few words. So, well, it's a sum as m and n are greater than equal to 0, y to the n, b to the m, h times a to the h times x to the n, everything is placed in the correct tensor factor. So y and b are placed in the I tensor factor, and a and x are placed in the right tensor factor, divided by m factorial times the quantum factorial of n. What's the quantum factorial of n? So, I don't know, I hate to say it, there is a bit of voodoo in these things. So a quantum integer, quantum k, is really 1 plus q squared up to q to the q minus 1, k minus 1. So you see, if you substitute q is equal to 1, then this is just a sum of k1s, so it's just k. And in fact, our q, I remind you, our q is e to the h bar epsilon. So if either of the small parameters, h bar or epsilon, is 0, q is equal to 1, and then the quantum integer is just the regular integer. You know, sometimes it's convenient to write this geometric series as this formula. Okay? Anyway, quantum factorials are products of quantum integers. So n sub q factorial is defined to be just the product of the quantum factorials 1 up to n. So for us, it's a certain weird power series in fact, weird power series in epsilon and h bar. But you know, if you don't substitute q to be the value that we've put into it, then it becomes a weird polynomial in q. Okay? Next, there is something called the quantum exponential. So the quantum exponential of z is the same as the exponential of z, except instead of dividing by n factorial, you divide by n quantum factorial. And then if you look at this formula, it more or less says that Rij is equal to the exponential of b times a. So b and a come with factors m, with powers m, and divided by m factorial. So it's the usual exponential of bij times the quantum exponential of xj, because yi comes with an n, xj comes with an n, and n is quantum n factorial. It's not quite this because the order of multiplication is wrong, the way I wrote it. Okay? So here the terms are in the order ybax, and here it's a slightly different order of terms. But other than that, it's roughly, that's why it's roughly. Again, completely legitimate to ask where is this coming from. Okay? Next. The next thing is convention. So remember that our strategy is to convert non-commutative algebras to commutative algebras to polynomial algebras. And then we need to order the generators. So our ordering will always be y-bax. Y, then b, then a, then x. Okay, and then there is a list of questions. Well, where does the name come from? How do we compute in this universal enveloping algebra? And so I gave you a definition, but if I wanted to check that something is true, that something is an R element, satisfies Young-Baxter, how do I do that? Where did QU come from? In what sense is it a quantization of CU? How is it related to the quantization of SL2? The funny formula for R, where is it coming from? How do we verify all the Hopf plus R properties of QU? So I gave you horrible definitions, but how do you check that these definitions satisfy the axioms I'm asserting they should satisfy? It's horrible. How do we compute in QU? And finally, suppose we succeed. Suppose I tell you how to compute in QU. The next question is this it? Notice that this is boldface it. Namely, do we have enough information here to construct a polynomial time computable strong tangle invariant which is homomorphic with respect to all the nice tangle operations? And the answer is, well, it seems like it's it. Okay? So we're motivated to answer all the questions before. Okay, let's start. Okay? So, okay, so I've laid out all the definitions. Now comes the work. And the definitions will stay in the handout, and you have a copy of the handout. So, okay. So, the first statement is completely general, a completely general statement about the algebras. And it's the statement that, so it's the Pbw Theorem, and it says that the universal enveloping algebra of a Lie algebra is always isomorphic as a vector space to a polynomial algebra. So hence, all these generating function techniques that we have apply. In fact, they apply in higher generality than we will use them. Okay? So, and let's make it precise. So it's the Poincare-Birkhoff-Witt theorem, which says that for any Lie algebra G, if you choose an order basis, call it uppercase X, which is really x1, x2, these are the basis for the Lie algebra. So for SL2 epsilon plus, by convention, x is always y, comma b, comma a, comma x. Okay? So our choice is always y, comma b, comma a, comma x, though we didn't need to. We could choose any other basis, any other order basis. And then, for each variable, introduce a commutative counterpart. So the only difference is that this is boldface and this is non-boldface. And you know, if I were to write it on the board, I would say that SL2 or the CU is the algebra generated by generators y, b, a, and x with hats on them instead of bold, modulo, well, the relations that are written on the handout. And now I'm looking at another algebra, namely the algebra of polynomials in variables y, b, a, and x, same names of variables but without the hats, or without being boldface. And then there is a map called the ordering map in the order y, b, a, x, which maps a polynomial in these variables to a polynomial in the corresponding variables here, written in the order first y's, then b's, then a's, then x. Here it's not significant what the order here is, and here it is. In general, we have an O sub x map going from polynomials in the commuting variables into the universal enveloping algebra, and it's defined by any monomial in the commuting variables becomes the corresponding monomial in the non-commuting variables, and here the order doesn't matter, and here the order does matter. Okay, and sorry, so far that's just definitions, and then the Pbw theorem says that this is an isomorphism of vector spaces. Okay? So, so the proof is pretty hard. The proof is surprisingly hard. Let me explain what goes into the proof. Yes?
Just a quick question about the other. So, what I understand is, so whenever maybe we want to go into the Lie algebra, we always have to take, so if we take any kind of word in the polynomial,
Yeah.
and we want to go into the Lie algebra, we always have to first order it before we go into that.
Yeah.
Don't
Except we're not going into the Lie algebra, we're going into the universal enveloping algebra of the Lie algebra.
Oh, okay.
Okay?
Yeah, okay.
I mean, in the Lie algebra, you cannot simply multiply as written here. In the Lie algebra, you only have brackets. And here I've allowed, the universal enveloping algebra is the Lie algebra where you've extended to allow multiplications.
Nice.
Okay? So here is the proof of Pbw, but of course I only mean this should be a sketch. Okay? Well, I'll use Weibach's language just because that's the algebra we care about, but the things I will say will be completely general. So I need to show, okay, so basically I have a map O sub x, O sub Weibach's, order in the order Weibach's, going from polynomials in y, b, a, and x into the associative algebra generated by y, b, a, and x modulo some relations. Okay? Now, I need to show that this map is onto and one-to-one. Well, that's how things go. So why is it onto? So suppose I have an arbitrary word in these letters. Allow me to drop the hats. Okay? So I have a word x, y, x, a, b, b, a, y, x. Okay? Well, I want to write it as a word in the form y to some power, b to some power, a to some power, x to some power. Okay? It's not of that form, right? But I want to write it in this form, so that if it was in this form, it would be clearly in the image. Okay? So I look at this word, and I find the first place where it's not of the right form. So it's x followed by y, but really in our ordering, y should be before x. That's bad. So I want to flip these two, right? But I already know that the bracket of x and y is equal to, God, what was it? B minus epsilon a? It really doesn't matter actually, but no, b plus epsilon a. B plus epsilon a. But it really doesn't matter. The point is that it's something. Okay? So this means that xy minus yx is b plus epsilon a. And it also means that xy is yx plus b plus epsilon a. So this word can be rewritten as xy x a b b a y x plus b plus epsilon a x a b b a y x. Okay? And this word is closer to the target. Closer to target. Yes?
So shouldn't it be yx now? Right.
Oh, of course, sorry, I flipped, so this should be yx, right, that's the point. You're right, sorry. It's closer to the target because, well, and this word has fewer letters. Namely, this word was of length 1, 2, 3, 4, 5, 6, 7, 8, 9, and this word is of length, this is a single letter, right? This is, well, it's actually a linear combination of two single letter things. Epsilon is just a parameter, A and B are the generators. So this is a single letter thing, and here we have another 7, so this is just 8 letters, which is 1 less than 9. So fewer letters means that by induction, this was treated before. So we don't need to worry about it. Okay, and now this one, so now yxx is fine, a is in the wrong place. A should be before x. So I move the a across the x. The price is something with fewer letters, which is dealt with by induction. And then I move the a across the other x, which again the price is something with fewer letters. And then I have yaxx. And then I just keep going. So I keep going like this, and I'm fine. And at the end I'm done. Okay? So we've proven that it's onto. Okay? Now I want to prove that it's 1-to-1. To prove that something is 1-to-1, I construct an inverse. Well, I sort of constructed an inverse, right? I told you if I have a word here, how to rewrite it, how to order it. The problem is that there are many different ways to order a word. I have chosen to first order this pair, but somebody else might have chosen to first order this pair. So the problem is to check whether this map is well defined. Okay? And the most interesting case turns out, suppose you have 3 letters, Z, Y, X, and the canonical ordering, the ordering you chose, is X, Y, Z. So there are 2 ways to order this, to reorder this. You can first reorder it to Y, Z, X, then reorder these 2. So Y, X, Z, and then reorder these 2, so it's X, Y, Z. Or, so here I chose to start with these 2, but I could have chosen to start with these 2. So I would get Z, X, Y, and here this again requires reordering the first pair. So it's X, Y, Z, sorry, X, Z, Y. And then by ordering the last pair, I get to here. But you see, every time you reorder, when I go from here to here, I pay a price, right? Like here, I mean, if I wanted to flip an x across a y, the price was something of lower order. So there is a price here, a price here, a price here, price, price, price. It better be that the sum of these 3 prices is equal to the sum of these 3 prices, or else the map is not well defined. And this turns out, so now you have to write everything explicitly and work a bit harder, and it turns out that this is implied by the Jacobi identity. So and in fact it's an if and only if. So basically the Jacobi identity is precisely the thing that makes the Pbw theorem true. So I will not go, I said I will only sketch the theorem, but, and I sketched it. What needs to come later is a detailed analysis of what are the prices that you're paying, and you find that they are the Jacobi identity. And then also further detailed analysis, well, this is one case. To show, you still have to show that this is the general case. That once you figured out how to order triples, everything else follows. So that's why Pbw is a bit hard. Okay. Well, I'm out of time, but I'll just say, the moment I have Pbw, everything is susceptible to our generating functions techniques. So in fact, I can write the generating functions of all the operations and then use our techniques to check all the properties. Well, I'll have to extend the techniques. But you know, if you think it's easy, then think again, because here is the generating function for multiplication. Okay? We'll have to check it next time. Okay, so see you on Wednesday.